Okay, differentiation, chain rule. It's one of my favorite parts of differentiation. Simple yet powerful. So hit pause, copy the lesson objective down. When you're ready, hit play again, and we'll define the chain rule. Okay, so if y is a function, when we differentiate it, we get dy over dx. What we can do then is we can say, if we introduce a new function u, dy divided by du times du over dx. And sometimes we need to split a function up to be able to differentiate it with respect to u. So that's our chain rule, super powerful, and we're going to look at an example in a second. So hit pause, write it down. When you're ready, hit play again, and we look at how we differentiate more complex functions. Right then, let's have a look at this example here. We've got, given that y is equal to 3x to the power of 4 plus x, all to the power of 5, find dy over dx using the chain rule. Let's do that. So y is equal to 3x to the power of 4 plus x, all to the power of 5. So what we say is, let u, it's a new function we're going to introduce, be equal to the x bit there, 3x to the power of 4 plus x. So everything in brackets there, we're going to equate that to u. That means y is now equal to, all of that is u, so it's u to the power of 5. Now I can differentiate y, dy with respect to u, and that's going to be equal to just a normal differentiation, 5u to the power of 4. Now we've said that u is equal to 3x to the power of 4 plus x. So if I differentiate u with respect to x, du over dx is equal to 4 times 3, so it'd be 12x to the power of 3 plus 1. So that's how our new function has interacted with y and x. So our chain rule is dy by dx is equal to dy by du times du by dx. So dy by du is 5u to the power of 4. I'm going to multiply that by du by dx, which is 12x cubed plus 1. So we're nearly there, except I want to put everything in terms of x. So I'm going to change my u, so that's going to be equal to 5. U is 3x to the power of 4 plus x, so 5 times 3x to the power of 4 plus x times 12x cubed plus 1. So that's a complex function, because we have 3x to the power of 4 plus x, all raised to the power of 5, differentiated by using a separate function u. So hit pause, copy the example down. When you're ready, hit play again, and we'll look at another example. Okay, so y equals sine to the power of 4 of x, find dy over dx. So we've got a complex function again, but I know I can differentiate sine of x. So what I'm going to do is, let's do it here. Y is equal to sine to the power of 4 of x. So I'm going to let u be equal to sine x. Now, if u equals sine x, that means y is equal to u to the power of 4. I can differentiate that with respect to u. dy over du is equal to 4u cubed. Now, u equals sine x. I can differentiate sine x. So du with respect to x is equal to cos x. Chain rule, dy over dx is equal to dy over du, oops, that's a y, times du over dx, which is equal to dy over du, take that from there, is 4u cubed. and I'll multiply that by du over dx, which is cos x. Now u is equal to sine x, so I'm going to substitute that back. 4 sine cubed x cos x. And that's dy over dx. Okay. Hit pause, write the example down. When you're ready, hit play again, and we'll look at another example. Okay, so let's have a look at this example. Y is equal to the square root of 5x squared plus 1. Find the gradient of the curve at 4, 9. So, what y is equal to the square root of 5x squared plus 1. Let's extend that square root there. That's the same thing as, if we want to differentiate it, it's much better to write it as 5x squared plus 1 to the power of a half. Now I'm going to let u be equal to 5x squared plus 1. Now I'm going to differentiate that. I know that u is equal to that part of it, so I'm going to say y is equal to u to the power of a half. I'm going to differentiate y with respect to u. dy over du is equal to a half of u to the power of minus a half. U equals 5x squared plus 1, so when I differentiate u with respect to x, I'm left with 10x. Chain rule, dy over dx is equal to dy over du times du over dx. So let's substitute. Dy over du is a half u squared, u to the power of minus a half even, times 10x. So sub back for u is 5x squared plus 1, so that's going to be a half 5x squared plus 1 to the power of minus a half. Now, times 10x. Negative power means reciprocal, so what I end up with is 10x divided by 2 times, well, it's the square root, isn't it, of 5x squared plus 1. So that's the first part. I've differentiated it. The second part, it wants the gradient at 4, 9. Let's change the color of my pen. So now find the gradient at 4, 9. So dy over dx is equal to, oh, hang on, didn't simplify that. 2 goes into 10. So that's equal to 5x over the square root of 5x squared plus 1. There we are. So that's equal to 5x divided by the square root of 5x squared plus 1. At this point, x is equal to 4, so let's sub in. So 5 times 4 all over the square root of 5 times 16 plus 1. So that's 20 over the square root of 81, which is 20 over 9. I'm happy with that. You can leave it as 20 over 9. Good. So hit pause, write the example down. When you're ready, hit play again. We'll look at another example. Okay. There's an additional rule you can use. Now, sometimes it's much easier to differentiate with respect to y than with respect to x. So in that case, we can use this. Now, dy over dx times dx over dy is simply 1, because they cancel each other out. So we can write dy over dx is equal to 1 over dx over dy. So sometimes we need to differentiate x with respect to y. Okay, so it's an additional rule. Sometimes we have to use it, and we're going to look at an example now. So write down this rule, and then when you're ready, hit play again. Let's look at an example. Right, so this is such an example. We've got to find the value of dy over dx. So the gradient at 2, 1, and the curve they've given us is y cubed plus y equals x. So let's write that here. Y cubed plus y equals x. Or if we write it the other way around, x is equal to y cubed plus y. So I can differentiate that with respect to y. So dx over dy, and just a normal differentiation then, gives me 3y squared plus 1. So that means then that dy over dx is going to be the reciprocal of that. So it's 1 over 3y squared plus 1. And that's how we've differentiated it. So that's part 1. Second part is the gradient at 2, 1. So at 2, 1, dy over dx is going to be equal to 1 over 3 times 1 squared plus 1. So that's just 3 plus 1. So it's 1 over 4, a quarter. So nice and simple. Hit pause, write the example down. And it's very useful sometimes when we can't separate them out. We haven't got a distinct y, we can just differentiate with respect to x. Okay. Hit pause, copy it down. When you're ready, hit play again. Okay, so a bit of classwork for you. What I want you to do now is, let's see, I think because it's brand new, don't skip anything and have a go. I think all of question 1 and all of question 2 will be important to get you more familiar, and then you can work your way through then. Okay? Good. It won't take you long once you get hold of the method. I'll attach the classwork